Every kid has dreamed of digging to China, but in 2025, we finally have the technology to find out how close we could actually get. With diamond-tip drill bits that can pulverize granite and automated drilling systems that operate continuously without human intervention, modern engineering has solved problems that seemed impossible just decades ago. Russia's Kola Superdeep Borehole reached 12,262 meters down, deeper than the Mariana Trench is deep, before extreme conditions force them to stop. But here's what nobody talks about. There's still one enemy that even our most advanced technology can't defeat. And it's waiting for us much closer to the surface than you think. To understand why, we need to start at the beginning and work our way down. Starting small, the first few meters. The first few meters beneath our feet contain the hidden infrastructure that makes modern life possible. Most people walk over this underground world without realizing that everything from their internet connection to their home's foundation exists in carefully planned layers just below the surface. At 8 meters down, we reach the standard depth for residential geothermal systems in 2025. These installations tap into the Earth's constant temperature at this depth, where the ground maintains a steady temperature regardless of surface weather conditions. In most locations, the temperature at 8 meters stays around 10 to 16 degrees Celsius year-round. Homeowners install loops of pipe at this depth to heat their houses in winter and cool them in summer. The excavation for a typical residential geothermal system creates trenches that could easily hide a single-story house. Modern metal detectors can penetrate down to similar depths, thanks to advances in electromagnetic field generation and signal processing. Professional archaeologists and treasure hunters use these devices to locate objects buried far deeper than previous generations of equipment could reach. The electromagnetic field generated by these detectors weakens with distance, but improved sensitivity allows detection of large metallic objects even at these depths. Continue down to 12 meters, and we discover the deepest recorded tree roots in urban environments. City trees face unique challenges because concrete, utility lines, and compacted soil force their roots to grow in unusual patterns. Some species have adapted by sending single roots straight down like biological drill bits, searching for water and nutrients below the urban landscape. These taproots can punch through small gaps in infrastructure and reach depths equivalent to a 4-story building. The roots at this depth are typically no thicker than a garden hose, but they can extend the tree's reach into soil layers that remain moist even during droughts. To put these depths in perspective, 12 meters equals the height of a typical 3-story apartment building. If you placed a standard city bus on its end, it would reach about 12 meters into the air. A telephone pole installed in 2025 typically stands 12 meters tall, which means our deepest tree roots extend as far underground as these poles reach above ground. A 2-story house with a standard roof peak measures roughly 8 meters from foundation to tip. So our geothermal systems extend slightly deeper than a house is tall. What makes these shallow depths remarkable is that humans could theoretically reach all of them using basic hand tools. Archaeological digs regularly reach 8 to 12 meters using nothing more sophisticated than shovels, picks, and buckets. The main limitation isn't technology, but time and effort. Professional excavation equipment makes these depths routine. A standard backhoe can easily reach 8 meters, while larger excavators extend to 12 meters or more. Construction crews dig to these depths daily for building foundations, utility installations, and infrastructure projects. The ground temperature at 12 meters fluctuates only slightly throughout the year, typically varying by just 2 to 3 degrees Celsius between summer and winter. This thermal stability makes these depths attractive for various applications beyond geothermal systems. Food storage facilities sometimes extend to these depths to take advantage of the natural cooling effect. Wine cellars built at 8 to 12 meters maintain consistent temperatures without mechanical cooling systems. Soil composition at these depths varies dramatically depending on location, but most areas still contain workable earth that responds predictably to excavation. Clay soils become more plastic and sticky, while sandy soils maintain their loose texture. Rocky areas present challenges, but standard construction equipment can break through most rock formations found at these shallow depths. Emergency services can easily reach accidents or cave-ins at these depths using conventional rescue equipment. fire departments carry ladders and rope systems capable of accessing 12-meter excavations. This accessibility means that construction work at these depths follows standard safety protocols without requiring specialized rescue teams on standby. Water tables in many regions exist somewhere between 5 and 12 meters, depending on local geology and seasonal rainfall. Excavations at these depths often encounter groundwater, which creates muddy conditions but rarely poses serious engineering challenges. Standard pumping equipment can handle the water infiltration typical at these levels. The air quality at 12 meters typically remains breathable without mechanical ventilation, though confined spaces require monitoring for carbon dioxide buildup and oxygen depletion. Workers can spend extended periods at these depths without specialized breathing equipment, assuming proper ventilation practices. For comparison, humans have dug much deeper by hand when necessary. The Woodingdean water well in the UK was dug entirely by hand in 1862 and reached 392 meters down. But modern drilling rigs have shattered all hand-digging records. Russia's Kola Superdeep Borehole reached 12,262 meters down using advanced drilling technology, proving that our machines can penetrate depths that would be impossible for manual excavation. These familiar depths represent just the beginning of our journey underground. The geothermal systems, tree roots, and basic infrastructure that exist in this shallow zone form part of the hidden foundation of modern life. Yet everything we've explored so far barely scratches the surface of human engineering capabilities. The natural features and simple installations at these depths seem substantial, but they represent only the most accessible layer of human construction beneath the surface. Underground landmarks we actually use. Beyond where we park cars, underground labs, and subways lie depths only machines can reach, starting at 2,197 meters, the deepest cave, and pushing further into mines and scientific boreholes. At 2,197 meters down, we encounter the Molina cave system, representing the deepest point that natural geological processes have carved into the Earth's crust. This cave system extends deeper than 7 Empire State Buildings stacked on top of each other. The cave reaches depths where atmospheric pressure increases significantly and where the temperature begins to rise noticeably due to geothermal heating. Explorers who venture into these depths require specialized equipment to manage the changing atmospheric conditions and the complete absence of natural light. The cave walls at 2,197 meters experience pressure from the weight of over 2 kilometers of rock above. This immense pressure creates geological conditions that differ substantially from surface environments. Water behavior changes at these depths, with different boiling points and flow characteristics that affect how underground rivers and pools form within the cave system. The air composition remains breathable, but the humidity and temperature create challenging conditions for human exploration. Cave exploration at these depths requires extensive logistical planning, because rescue operations become extremely complex. Emergency teams must transport equipment through narrow passages and vertical drops that extend for over 2 kilometers. The time required to evacuate an injured person from 2,197 meters underground can exceed 24 hours even with optimal conditions and experienced rescue teams. Moving deeper to 4,000 meters, we reach the operational depth of the Tautona mine in South Africa, one of the deepest mining operations on Earth. This gold mine extends so far underground that miners must travel the equivalent distance of driving from one city to another just to reach their work areas. The journey from surface to the deepest working levels takes over an hour using high-speed mining elevators. At 4,000 meters underground, the rock temperature reaches approximately 60 degrees Celsius due to geothermal heating. The mine requires massive refrigeration systems that pump chilled air through kilometers of ventilation shafts to create working conditions that humans can survive. These cooling systems consume enormous amounts of energy and represent one of the largest operational expenses for deep mining operations. The rock pressure at 4,000 meters creates conditions where tunnel walls can collapse without warning. Mining engineers install extensive support systems using steel beams, concrete reinforcement, and rock bolts that extend deep into surrounding stone. The pressure is so intense that solid rock behaves almost like a thick liquid, slowly flowing and deforming over time. Miners must constantly monitor tunnel integrity because the mountain literally tries to close the excavated spaces. Workers at these depths face unique physiological challenges beyond just heat and pressure. The human body responds differently to the atmospheric conditions found 4,000 meters underground. Blood circulation changes, and workers require acclimatization periods. Similar to high-altitude training, the mine operates with strict rotation schedules because extended exposure to these conditions affects human performance and safety. Transportation of materials to 4,000 meters requires specialized equipment capable of handling the extreme conditions. Standard construction materials behave differently under the pressure and temperature found at these depths. Steel becomes more brittle, concrete curing processes change, and electronic equipment requires additional protection from the harsh environment. The deepest point that represents the absolute limit of human engineering achievement underground is 12,262 meters, reached by Russia's Kola Superdeep Borehole. This scientific drilling project pushed deeper into the earth than any previous human construction. The borehole extends deeper than the deepest ocean trenches and represents humanity's deepest penetration into the planet's crust. The Kola project encountered conditions that challenged every assumption about deep Earth geology. At 12,262 meters, the temperature reached 180 degrees Celsius, much hotter than the expected 100 degrees Celsius that scientists had predicted. The rock at these depths behaved more like plastic than solid stone, making drilling extremely difficult. The pressure was so intense that the borehole walls constantly tried to close, requiring continuous intervention to keep the hole open. The drilling equipment used for the Kola project represented the most advanced technology available for deep earth penetration. Diamond-tip drill bits capable of cutting through the hardest rock formations wore out rapidly under the extreme conditions. The drilling fluid used to cool the equipment and remove rock debris had to be specially formulated to remain stable at temperatures that would destroy conventional materials. Communication with equipment at 12,262 meters required specialized systems because standard electronic equipment fails under the pressure and temperature conditions found at these depths. The drilling operation used hardened electronics and redundant communication systems to maintain contact with surface operations. Even with these precautions, equipment failure was common and expensive to repair or replace. The Kola borehole revealed that the deep earth contains conditions far more extreme than surface-based theories had predicted. The discovery of microscopic life forms at depths previously thought to be sterile challenged scientific understanding of where life can exist. The presence of water at depths where geological models suggested only dry rock should exist forced scientists to revise their theories about deep earth processes. These three landmarks, the 2,197-meter Molina Cave, the 4,000-meter Tautona Mine, and the 12,262-meter Kola Superdeep Borehole, represent the absolute limits of where humans have successfully operated or built structures underground. Each depth required increasingly sophisticated technology and represented exponentially greater engineering challenges. The progression from natural caves to mining operations to scientific boreholes shows how human technology has pushed progressively deeper into the earth. Each achievement required solving problems that seemed impossible with previous generations of equipment and techniques. The temperature, pressure, and geological conditions at these depths create environments more hostile than outer space in many ways. Yet even these remarkable achievements pale in comparison to the theoretical depths that modern 2025 technology might reach. The lessons learned from the Kola project and deep mining operations have informed new approaches to deep drilling that could potentially reach even greater depths. However, the extreme conditions encountered at these record-breaking depths reveal that we are approaching fundamental limits imposed by the physics of deep earth environments. Human presence becomes increasingly impractical as we venture deeper underground, and these landmark depths represent the transition point where only our most advanced machines can operate effectively. Where machines take over. At depths beyond 200 meters, the air becomes unbreathable and only autonomous systems can operate effectively. These depths mark the transition where drilling robots, smart measurement while drilling tools, and AI-controlled equipment take complete control of operations. Modern drilling automation systems, like Halliburton's Logix platform integrated with Sequel's Drilltronics, represent the cutting edge of this technology, enabling autonomous directional drilling with automated wellbore hydraulics and dynamic surface drilling rig equipment control. Operators can enhance drilling parameters in real time and accurately position wells with a press of a single button, demonstrating how far automation has advanced in 2025. The integration of artificial intelligence and Internet of Things technologies has revolutionized these deep operations. Smart drilling software platforms feature AI-powered search capabilities and operation optimization recommendations that analyze conditions faster than human operators could process the information. IoT-enabled drilling equipment allows comprehensive real-time data collection, monitoring, and remote control through sensors that track critical parameters including temperature, vibration, torque, and depth. Predictive maintenance, powered by cloud-based analytics, has become essential for maintaining operations at these isolated depths, where equipment failure means permanent loss of expensive machinery. China's ShenDitake 1 borehole in the Taklamakan Desert demonstrates the capabilities of modern automated drilling systems. This project reached 10 kilometers deep and serves as a testbed for extreme drilling technologies, providing valuable data on managing high-pressure, high-temperature conditions deep underground. The project relies entirely on automated systems because human operators cannot survive the conditions encountered at these depths. The success of such ultra-deep drilling operations hinges on technological advancements, robust engineering techniques, and precise scientific planning that eliminates human intervention from the drilling process. Advanced drilling equipment operating at these depths includes self-calibrating drill bits that use smart sensors to monitor wear levels and make real-time adjustments to ensure optimal cutting performance. High-performance drill bits featuring nano-coating technology, particularly titanium aluminum nitride coatings, demonstrate remarkable improvements in durability, reduced friction, and enhanced heat resistance under extreme conditions. These smart bits can detect when cutting efficiency drops below optimal thresholds and automatically adjust their operation to maintain performance without stopping the drilling process. Hybrid drilling methods combine traditional mechanical drilling with advanced technologies like laser-assisted drilling and ultrasonic vibration techniques. These approaches prove especially valuable when working with delicate or high-hardness materials that would quickly destroy conventional cutting tools. The automated systems can switch between cutting methods based on real-time analysis of material properties encountered during excavation, making decisions that optimize performance for specific geological conditions. Heat-resistant drilling fluids represent another critical advancement for deep automated operations. These specialized fluids maintain their viscosity under extreme thermal stress exceeding 400 degrees Celsius, conditions that would incapacitate human workers instantly. The fluids must continue functioning properly while carrying rock debris to the surface and cooling drilling equipment that operates continuously for weeks without maintenance breaks. Standard drilling fluids would break down completely under these temperature conditions, making these advanced formulations essential for deep drilling success. Communication systems at these depths require fiber optic cables because radio waves cannot penetrate through hundreds of meters of soil and rock. The cables must withstand enormous soil pressure and potential crushing forces that increase with depth. Signal boosters positioned at regular intervals throughout the vertical cable runs maintain data transmission quality. But communication delays mean that automated systems must operate with greater independence and make critical decisions without real-time human oversight. The structural integrity of boreholes becomes increasingly challenging as automated drilling systems push deeper. Rocks at extreme depths experience stresses that can lead to unexpected fractures and collapses, requiring constant monitoring through automated systems that can respond faster than human operators. The pressure is so intense that solid rock behaves almost like a thick liquid, slowly flowing and deforming over time. Automated support systems must continuously adjust to maintain borehole stability without human intervention. Environmental considerations increasingly influence the development of these automated drilling technologies. Energy-efficient motors with power-saving mechanisms have become standard in modern drilling equipment because power consumption becomes critical when operating hundreds of meters underground. The industry has transitioned toward biodegradable lubricants made from plant-based oils, which offer similar performance levels to traditional petroleum-based products, while being environmentally safer if equipment failures result in spills at these isolated depths. Advanced noise-dampening technologies and vibration control systems make modern automated drilling rigs quieter and more stable, improving equipment longevity and ensuring compliance with environmental regulations. These systems operate without human oversight, automatically adjusting their operation to minimize environmental impact while maintaining drilling efficiency. The vibration control becomes especially important at extreme depths, where excessive vibration can destabilize the surrounding rock formation. Machine learning algorithms analyze soil composition, structural stability, and equipment performance to optimize operations continuously. These systems learn from experience and improve their decision-making capabilities over time without human programming updates. The AI can predict equipment failures days in advance and automatically schedule maintenance operations to prevent costly breakdowns that would be impossible to repair at these depths. The autonomous systems operating at these depths represent the absolute limit of current robotic technology. Communication delays, equipment reliability issues, and environmental challenges compound rapidly as depths increase. Emergency response capabilities become meaningless because conventional rescue equipment cannot reach these depths, and human rescue operations would require specialized equipment costing millions of dollars and taking hours to deploy. Standard drill bits wear down quickly under the high temperatures and stress encountered at these depths, making diamond-impregnated bits essential for sustained operations. Even these advanced bits require continuous monitoring through embedded sensors that track performance and automatically adjust cutting parameters to extend operational life. The extreme conditions push artificial intelligence and robotic systems to their current technological limits, creating operational scenarios that test the boundaries of what machines can accomplish independently. Beyond these machine-dominated depths, we approach territory where even the most advanced automated systems begin to struggle. Yet somehow humans have still managed to create functional spaces in these extreme underground environments. The deepest human-made spaces. The deepest concert ever held underground took place at 1,410 meters in Finland, where the band Agonizer performed in conditions that would challenge even the most advanced sound engineering. This remarkable achievement demonstrates how humans have pushed entertainment venues into depths where the natural acoustic properties create sound experiences impossible to replicate on the surface. The solid rock surrounding these performance spaces eliminates all external noise interference, creating recording studio conditions that cost millions to achieve artificially above ground. Yet even these extraordinary entertainment venues pale in comparison to the operational depths, where humans work daily under the most extreme conditions imaginable. At 4,000 meters underground, the Tautona mine in South Africa represents the absolute limit of human occupation beneath the Earth's surface. This gold mining operation extends so deep that workers must travel the equivalent distance of driving between cities just to reach their work areas. The journey from surface to the deepest working levels takes over an hour using high-speed mining elevators, and workers experience ambient temperatures that regularly exceed 60 degrees Celsius. The mine requires massive refrigeration systems that pump chilled air through kilometers of ventilation shafts to create working conditions that humans can survive. These cooling systems consume enormous amounts of energy and represent one of the largest operational expenses for the mining operation. Workers at 4,000 meters face unique physiological challenges beyond just heat and pressure. The human body responds differently to the atmospheric conditions found at these depths, requiring acclimatization periods similar to high-altitude training. The rock pressure at 4,000 meters creates conditions where tunnel walls can collapse without warning. Mining engineers install extensive support systems using steel beams, concrete reinforcement, and rock bolts that extend deep into surrounding stone. The pressure is so intense that solid rock behaves almost like a thick liquid, slowly flowing and deforming over time. Miners must constantly monitor tunnel integrity because the mountain literally tries to close the excavated spaces. Transportation of materials to 4,000 meters requires specialized equipment capable of handling the extreme conditions. standard construction materials behave differently under the pressure and temperature found at these depths. Steel becomes more brittle, concrete curing processes change, and electronic equipment requires additional protection from the harsh environment. Emergency evacuation procedures account for the time required to bring workers from maximum depth to surface, with backup systems designed to operate during power failures or equipment malfunctions. The ventilation systems at Tautona move millions of cubic meters of air hourly to maintain breathable conditions and remove heat generated by equipment and human activity. Air conditioning systems, designed for these depths, consume more electricity than small cities, operating continuously to prevent heat-related health emergencies among workers. The mine operates with strict rotation schedules because extended exposure to these conditions affects human performance and safety. Medical monitoring systems track vital signs continuously and trigger emergency responses when workers show signs of heat exhaustion or pressure-related health problems. Emergency medical facilities positioned at intermediate depths provide treatment capabilities for conditions that develop during deep underground work. The medical staff includes specialists trained in pressure-related medicine and emergency procedures adapted for extreme depth environments. The engineering required to maintain habitable conditions at 4,000 meters costs millions of dollars per installation and requires continuous maintenance by specialized technical teams. Emergency response capabilities diminish rapidly at these depths because conventional rescue equipment cannot operate effectively under these extreme conditions. The combination of pressure, temperature, and environmental challenges creates conditions that approach the boundaries of what human physiology can endure even with technological assistance. Beyond 4,000 meters, human occupation becomes impossible regardless of technological support. The conditions encountered at greater depths exceed the limits of what protective equipment can overcome and what the human body can survive. At these extreme depths, only our most advanced drilling technology can operate, and even machines begin to struggle against the increasingly hostile environment. The transition from human-occupied spaces to machine-only operations occurs gradually as depths increase beyond the 4,000-meter threshold. The temperature rises dramatically with each additional kilometer, reaching levels that would instantly incapacitate unprotected humans. The pressure increases to the point where standard materials fail and specialized alloys become necessary for any equipment to function. The Kola Superdeep Borehole at 12,262 meters represents the deepest point that human technology has ever reached into the Earth's crust. This scientific drilling project encountered conditions that challenged every assumption about deep Earth geology. At maximum depth, the temperature reached 180 degrees Celsius, much hotter than the expected 100 degrees Celsius that scientists had predicted. The rock at these depths behaved more like plastic than solid stone, making drilling extremely difficult. The drilling equipment used for the Kola project represented the most advanced technology available for deep earth penetration. Diamond-tip drill bits capable of cutting through the hardest rock formations wore out rapidly under the extreme conditions. The drilling fluid used to cool the equipment and remove rock debris had to be specially formulated to remain stable at temperatures that would destroy conventional materials. Communication with equipment at 12,262 meters required specialized systems because standard electronic equipment fails under the pressure and temperature conditions found at these depths. The drilling operation used hardened electronics and redundant communication systems to maintain contact with surface operations. Even with these precautions, equipment failure was common and expensive to repair or replace. The Kola borehole revealed that the deep earth contains conditions far more extreme than surface-based theories had predicted. The discovery of microscopic life forms at depths previously thought to be sterile challenged scientific understanding of where life can exist. The presence of water at depths where geological models suggested only dry rock should exist forced scientists to revise their theories about deep earth processes. These achievements demonstrate that while humans can work at 4,000-meter depths in specialized mining operations, technology alone must handle anything deeper. The 12,262-meter Kola borehole shows that even our most advanced drilling systems approach their operational limits long before reaching the Earth's mantle. The extreme conditions encountered at these record-breaking depths reveal fundamental records that challenge these engineering achievements mark the beginning of humanity's quest to break absolute drilling depth records, where the sole objective becomes reaching as deep as possible regardless of cost or practical application. The current world record belongs to Russia's Kola Superdeep Borehole, which reached 12,262 meters in 1989. This scientific drilling project pushed deeper into the Earth's crust than any previous human construction, extending further underground than the deepest ocean trenches reach below sea level. The Kola project encountered conditions that challenged every assumption about deep Earth geology. At maximum depth, the temperature reached 180 degrees Celsius, much hotter than the expected 100 degrees Celsius that scientists had predicted. The rock at these depths behaved more like plastic than solid stone, making drilling extremely difficult and ultimately forcing the project to halt. The drilling equipment used for the Kola project represented the most advanced technology available for deep earth penetration at the time. Diamond-tipped drill bits capable of cutting through the hardest rock formations wore out rapidly under the extreme conditions. The drilling fluid used to cool the equipment and remove rock debris had to be specially formulated to remain stable at temperatures that would destroy conventional materials. Communication with equipment at 12,262 meters required specialized systems because standard electronic equipment fails under the pressure and temperature conditions found at these depths. The Kola borehole revealed that the deep Earth contains conditions far more extreme than surface-based theories had predicted. The discovery of microscopic life forms at depths previously thought to be sterile challenged scientific understanding of where life can exist. The presence of water at depths where geological models suggested only dry rock should exist forced scientists to revise their theories about deep Earth processes. The project was eventually sealed off due to safety violations, environmental concerns, and financial constraints when drilling ceased in 1992 because temperatures were twice as expected and drilling equipment could not cope with the heat. China has emerged as the new leader in extreme depth drilling with ambitious projects that aim to surpass the Kola record. The ShenDitake 1 borehole in the Tarim Basin reached 10,000 meters in March 2024. Becoming Asia's deepest vertical well. This project serves as a testbed for extreme drilling technologies and provides valuable data on managing high-pressure, high-temperature conditions deep underground. The success of ShenDitake 1 demonstrates how far drilling technology has advanced since the Soviet era, incorporating modern material science, computer-controlled drilling systems, and advanced drilling fluid chemistry. The data gained from ShenDitake 1 directly contributes to China's next ambitious target, a 15,000-meter borehole that would shatter all previous drilling records. This project represents part of China's broader strategy to enhance energy security by exploring geothermal and other deep earth resources. Scientists also plan to use the borehole as a natural laboratory to study subsurface conditions, seismic activity, and the structure of the Earth's layers, which remain largely uncharted at such depths. The technological challenges of reaching 15,000 meters require solutions that push beyond current engineering capabilities. Advanced drilling systems must incorporate AI integration, automated drilling tools, and sustainability innovations that improve efficiency while reducing environmental impact. The breakthrough in automated drilling systems by companies like Halliburton and Seacal represents significant advancement that could transform drilling operations at these extreme depths. AI-powered search capabilities and operation optimization recommendations analyze conditions faster than human operators could process the information. Modern drilling equipment operating at record depths includes self-calibrating drill bits that use smart sensors to monitor wear levels and make real-time adjustments to ensure optimal cutting performance. High-performance drill bits featuring nano-coating technology, particularly titanium aluminum nitride coatings, demonstrate remarkable improvements in durability, reduced friction, and enhanced heat resistance under extreme conditions. These smart bits can detect when cutting efficiency drops below optimal thresholds and automatically adjust their operation to maintain performance without stopping the drilling process. The The challenges of extreme depth drilling include tool runout, walking, chip evacuation, and cooling. Tool runout causes the drill tip to orbit around the axis of rotation, which increases the diameter of the hole and reduces drilling efficiency. Walking occurs when the drill tip first makes contact with the workpiece, causing the hole to be drilled at an angle rather than straight down. Chip evacuation becomes increasingly difficult as depth increases because chips can wrap around the drill flutes and accumulate, causing temperature buildup and drill failure. Heat-resistant drilling fluids represent a critical advancement for record-breaking drilling operations. These specialized fluids must maintain their viscosity under extreme thermal stress exceeding 400 degrees Celsius while continuing to carry rock debris to the surface and cool drilling equipment that operates continuously for months without maintenance breaks. Standard drilling fluids would break down completely under these temperature conditions, making advanced formulations essential for extreme depth success. Communication systems at record depths require fiber optic cables because radio waves cannot penetrate through thousands of meters of soil and rock. The cables must withstand enormous soil pressure and potential crushing forces that increase dramatically with depth. Signal boosters positioned at regular intervals throughout the vertical cable runs maintain data transmission quality. But communication delays mean that automated systems must operate with greater independence and make critical decisions without real-time human oversight. The structural integrity of boreholes becomes increasingly challenging as drilling systems push toward record depths. Rocks at extreme depths experience stresses that can lead to unexpected fractures and collapses, requiring constant monitoring through automated systems that can respond faster than human operators. The pressure becomes so intense that solid rock behaves almost like a thick liquid, slowly flowing and deforming over time. Automated support systems must continuously adjust to maintain borehole stability without human intervention. The economic costs of record-breaking drilling projects reach hundreds of millions of dollars and require years of continuous operation. The specialized equipment, exotic materials, and expert personnel needed for these projects exist in extremely limited quantities worldwide. Only a handful of drilling contractors possess the technology and expertise needed to attempt record-setting depths, creating a bottleneck that limits the number of extreme depth projects that can proceed simultaneously. The progression from the 12,262-meter Kola record to China's planned 15,000-meter target represents a significant technological leap that requires fundamental advances in material science, artificial intelligence, and drilling system design. Each additional kilometer deeper demands exponentially more sophisticated engineering solutions and dramatically higher costs. The engineering challenges multiply because every system must work perfectly under conditions that provide no margin for error. Yet despite these remarkable achievements and ambitious future targets, every drilling project that attempts to break depth records eventually encounters the same fundamental obstacle that has limited human penetration into the earth for decades: the temperature barrier. This fundamental obstacle reveals itself as extreme heat that destroys even the most advanced drilling equipment long before reaching theoretical depth targets. The Kola Superdeep Borehole encountered the reality of this temperature barrier at 12,262 meters when drilling equipment faced unexpected temperatures of 180 degrees Celsius. Scientists had predicted temperatures around 100 degrees Celsius at that depth, but the actual conditions proved far more hostile than theoretical models suggested. The extreme heat accelerated equipment degradation and contributed directly to the project's eventual halt, demonstrating how temperature creates an insurmountable engineering challenge that budget and expertise cannot overcome. At 180 degrees Celsius, electronic components experience catastrophic failure because semiconductor materials lose their electrical properties when heated beyond design specifications. Circuit boards warp under thermal stress, solder joints begin melting, and microprocessors shut down completely. The integrated circuits that control modern drilling operations cannot function at these temperatures, leaving operators without the computerized systems that make precision drilling possible. Drilling fluid undergoes chemical breakdown at these temperatures that destroys its cooling and lubricating properties. Standard drilling mud contains water-based compounds that boil away rapidly, leaving behind thick sludge that cannot circulate through drill pipes. The chemical bonds holding specialized high-temperature fluids together rupture under sustained heat exposure, creating byproducts that clog drilling equipment and damage pump mechanisms. Even synthetic drilling fluids, designed specifically for extreme conditions, begin losing the viscosity needed to carry rock cuttings away from the drill bit. Steel drill pipes lose approximately 30% of their tensile strength at 180 degrees Celsius, making them vulnerable to catastrophic failure under the weight and stress of deep drilling operations. The metallurgical changes in steel occur gradually, but irreversibly, as sustained heat exposure alters the crystalline structure of the metal. High-strength steel alloys begin experiencing creep deformation, where the material slowly stretches under load until structural failure occurs without warning. Chinese drilling projects have pushed deeper than Kola while encountering similar temperature challenges. The ShenDitake 1 borehole reached 10,000 meters and provided valuable data about managing high-temperature conditions at extreme depths. These projects demonstrate that modern drilling technology has advanced significantly since the Soviet era, incorporating improved material science, computer-controlled drilling systems, and advanced drilling fluid chemistry. However, they also confirm that temperature remains the primary limiting factor for extreme depth drilling. Scientists are developing heat-resistant drilling fluids that maintain their viscosity under extreme thermal stress exceeding 400 degrees Celsius to help cool drill bits and stabilize borehole walls. These experimental fluids cost over $2,000 per barrel and require specialized handling equipment that adds millions to project costs. The circulation systems needed to pump these fluids through thousands of meters of pipe require pumps rated for extreme temperature applications, which weigh significantly more and consume substantially more power than conventional pumping equipment. Diamond-enhanced drill bits begin experiencing thermal degradation as temperatures approach 200 degrees Celsius. The chemical bonds holding synthetic diamonds to the cutting surface weaken under sustained heat exposure. The metal matrix holding diamond particles undergoes thermal expansion that creates stress concentrations around individual diamond crystals. These stress concentrations cause diamonds to fracture and separate from the cutting surface, reducing drilling efficiency and requiring frequent bit replacement. Looking toward future drilling targets, companies like Quaise anticipate encountering temperatures around 500 degrees Celsius at depths of 15,000 meters. At these projected temperatures, most metals experience significant creep deformation that makes them unsuitable for structural applications requiring dimensional stability. The yield strength of high-grade steel alloys drops to less than 50% of their room temperature values, making structural failure inevitable under drilling loads. Ceramic materials that resist high temperatures become brittle and prone to thermal shock at 500 degrees Celsius. The thermal expansion mismatch between different ceramic components creates internal stresses that lead to cracking and component failure. Advanced ceramic composites designed for aerospace applications can survive these temperatures briefly, but sustained exposure causes microstructural changes that degrade their mechanical properties over time. The pumping systems required to circulate cooling fluids face impossible engineering challenges at extreme depths and temperatures. The pumps must generate pressures thousands of times greater than atmospheric pressure while operating in environments that exceed the operational limits of most materials. Pump seals fail rapidly under these combined temperature and pressure conditions, causing fluid leakage that disables cooling systems. The power requirements for these pumping systems exceed the electrical generation capacity of most drilling rigs, requiring massive surface power plants to supply adequate electricity. Current cooling technology can only delay equipment failure rather than prevent it entirely. Refrigeration systems powerful enough to cool equipment at extreme depths would require energy inputs that exceed the power generation capacity of most small cities. The physics of heat transfer works against any cooling system at extreme depths because pumping coolant through thousands of meters of pipe requires overcoming friction losses that increase exponentially with distance and fluid velocity. The cooling fluid itself absorbs heat during circulation, requiring massive heat exchangers at the surface to remove thermal energy before recirculation. The thermal mass of thousands of meters of drill pipe and associated equipment exceeds the cooling capacity of any practical refrigeration system. Heat generation from friction, compression, and geothermal sources will always exceed the cooling capacity of mechanical systems operating at these depths. The success of ultra-deep drilling beyond 15 kilometers hinges on technological advancements, robust engineering techniques, and precise scientific planning to withstand extreme heat, pressure, and geological instability. However, the fundamental thermodynamic challenges posed by extreme temperatures represent limitations that cannot be overcome through engineering innovation alone. The laws of physics dictate that heat will always accumulate faster than any mechanical cooling system can remove it at these depths. Even theoretical future materials cannot overcome these fundamental thermodynamic challenges. The temperature barrier represents a hard physical limit that stops drilling ambitions regardless of technological advancement or financial investment. Yet temperature alone does not tell the complete story of why extreme depth drilling becomes impossible, because heat works in combination with another force that compounds these challenges exponentially: the pressure problem. Pressure likewise blocks us from reaching extreme depths. At the Kola Superdeep Borehole's record depth of 12,262 meters, pressure was already too intense for standard equipment to operate reliably. The overlying rock at this depth creates crushing forces that exceed the design specifications of conventional drilling systems. Steel components that perform flawlessly at surface conditions begin experiencing stress concentrations that approach their structural limits. The pressure increases predictably with depth, adding approximately 27 kilopascals for every meter deeper. But the engineering challenges grow exponentially because materials reach failure thresholds that create cascading structural problems. The drill string itself becomes vulnerable to compression failure as depths increase beyond current records. At 15,000 meters, the projected target for China's next drilling project, the pressure would exceed the structural capacity of standard drill pipe materials. The weight of the drill string alone creates tensile stresses that approach the breaking point of high-strength steel alloys, and the external pressure from surrounding rock compounds these stresses to create failure conditions that no conventional drilling system can withstand. The physics of pressure increase with depth follows a predictable pattern based on the density of overlying rock and gravitational acceleration. Each additional meter of depth adds weight that must be supported by drilling equipment and borehole walls. The cumulative effect creates pressure conditions that attack materials from all directions simultaneously, preventing the formation of load-bearing structures that could resist the crushing forces. Unlike surface applications where pressure loads can be distributed through structural design, deep drilling creates hydrostatic loading conditions that compress materials uniformly from every direction. Steel alloys that provide exceptional performance in surface construction applications lose their structural integrity under the pressure conditions found at extreme depths. The atomic bonds holding metal crystals together begin failing as external pressure forces exceed the internal cohesive forces that give metals their strength. High-strength steel that costs thousands of dollars per ton becomes structurally inadequate when subjected to the crushing forces present at depths beyond 15,000 meters. The metallurgical properties that make these materials valuable for conventional applications prove insufficient against the relentless compression forces found in deep drilling environments. Advanced materials like titanium alloys and specialized composites face similar limitations under extreme pressure conditions. Titanium maintains its strength at high temperatures, but succumbs to pressure-induced deformation that renders it structurally useless at extreme depths. Carbon fiber composites that demonstrate exceptional strength-to-weight ratios in aerospace applications experience compression failure when subjected to the hydrostatic loading conditions present in deep boreholes. The molecular structure of these advanced materials cannot withstand the external forces that attempt to compress their atomic arrangements beyond elastic limits. The pressure creates stress concentrations that exceed the yield strength of every known material currently available for drilling applications. Even the strongest substances developed for extreme environments fail when subjected to the combined loading conditions present at depths approaching 15,000 meters. The failure occurs not through gradual degradation, but through catastrophic structural collapse that happens almost instantaneously when pressure loads exceed material capabilities. Pressure and temperature work together to create impossible conditions that exceed the capabilities of any current engineering solution. The combination of extreme heat and crushing pressure creates an environment where materials experience simultaneous thermal expansion and compressive loading that guarantees structural failure. Thermal expansion causes materials to grow larger, while pressure forces attempt to compress them into smaller volumes, creating internal stress concentrations that lead to rapid material failure. This thermomechanical interaction prevents any material from maintaining structural integrity under the combined assault of heat and pressure. The strongest materials available in 2025 cannot handle this combined assault because the failure mechanisms reinforce each other rather than operating independently. High-temperature materials that resist thermal degradation become more brittle and prone to pressure-induced cracking. Pressure-resistant materials that maintain structural integrity under compression become more susceptible to thermal degradation that weakens their atomic structure. The interaction between temperature and pressure creates failure modes that exceed the design capabilities of materials optimized for either thermal or mechanical loading alone. At extreme depths, the Earth's crust itself becomes plastic-like under the combined pressure and temperature conditions. The rock formations that appear solid and stable at surface conditions begin flowing like thick liquid when subjected to the enormous pressures found at depths beyond current drilling records. This plastic deformation occurs because the pressure exceeds the yield strength of rock materials, causing them to deform continuously under load rather than maintaining rigid structural properties. Granite, limestone, and other rock types that provide stable foundation materials for surface construction lose their structural integrity and begin behaving like viscous fluids. The plastic behavior of rock at these depths makes borehole stability extremely difficult to maintain because the surrounding material continuously flows inward to fill any void space created by drilling operations. Maintaining open boreholes becomes increasingly challenging as the plastic rock deformation creates loading conditions that attack support structures from all directions. Steel casing systems that successfully support boreholes at moderate depths face crushing forces that exceed their structural capacity when subjected to the continuous inward pressure from plastic rock deformation. Supporting structures like casing systems become inadequate at these depths because the external pressure exceeds the structural capacity of any practical support system. The continuous inward pressure from plastic rock deformation creates loading conditions that no structural support system can resist indefinitely. Conventional casing designs that work effectively at moderate depths fail catastrophically when subjected to the extreme pressure conditions present at depths approaching the limits of current drilling technology. The engineering challenges multiply exponentially with each additional kilometer of depth because pressure-related failures cascade through interconnected systems. A failure in one component creates additional loading on remaining systems that accelerates their failure in a domino effect that destroys entire drilling operations. The redundancy in backup systems that provide safety margins in conventional drilling become inadequate when subjected to the extreme conditions present at record-breaking depths. Combined with the temperature barrier, pressure creates a permanent obstacle that cannot be overcome through improved design, better materials, or more advanced manufacturing techniques. The laws of physics governing material behavior under extreme conditions establish definitive boundaries for drilling capabilities that represent fundamental rather than temporary technological constraints. These physical limitations raise the ultimate question: Even if we could somehow overcome every practical constraint, what would represent the absolute theoretical maximum depth that the laws of physics would permit? Scientists have calculated theoretical limits for drilling depth. But these calculations reveal more about the impossibility of extreme depth drilling than any realistic engineering targets. Even with unlimited resources and materials that violate known physical laws, the absolute theoretical maximum depth before complete hole collapse reaches approximately 60,000 meters under perfect conditions that assume technology that simply does not exist. This theoretical limit requires materials with infinite strength, cooling systems that defy thermodynamics, and drilling equipment that operates flawlessly under impossible conditions. Even under these fantasy scenarios, the Earth itself sets the boundary through geological processes that make deeper drilling physically impossible. The rock and soil at 60,000 meters depth exist under such extreme pressure and temperature that they behave like thick liquid rather than solid material. Any hole drilled into this plastic-like substance would seal itself closed faster than drilling equipment could remove material. To understand how insignificant this theoretical maximum really is, consider that Earth measures 6,371,000 meters from surface to center. The theoretical maximum depth of 60,000 meters represents less than 1% of the distance to Earth's core. Humanity could theoretically penetrate only 0.94% of the way to the center of our own planet, even with perfect technology that violates known physical laws. This calculation reveals the staggering scale difference between human engineering capabilities and the size of the Earth itself. The 60,000-meter theoretical maximum assumes materials that maintain structural integrity under conditions that would destroy any known substance. These hypothetical materials would need to resist temperatures approaching 700 degrees Celsius while withstanding pressures that exceed 6,000 times atmospheric pressure. No material exists today or likely to exist in the foreseeable future that could survive these combined assaults. The theoretical calculation serves more as a physics exercise than a practical engineering goal because it requires materials that contradict fundamental principles of chemistry and metallurgy. Real-world limitations make even reaching 40,000 meters nearly impossible with current or projected technology. The Kola Superdeep Borehole reached only 12,262 meters before heat and pressure forced abandonment of the project. The temperatures encountered exceeded expectations by 80 degrees Celsius, and the rock formations proved more challenging than anticipated. Extending drilling operations to 40,000 meters would require overcoming temperature and pressure conditions roughly 3 times more severe than those that stopped the Kola project. The engineering challenges at 40,000 meters include developing cooling systems that can remove heat from equipment operating in 400-degree environments while pumping coolant through 40 kilometers of vertical pipe. The energy requirements for such cooling systems would exceed the electrical output of most power plants, making the operation economically impossible even with unlimited funding. Additionally, the drilling equipment would need to support its own weight across 40 kilometers of vertical distance, while generating enough torque to cut through rock formations that become increasingly hard and abrasive with depth. Modern drilling technology represents the culmination of centuries of engineering advancement. Yet, our deepest achievements barely penetrate Earth's outermost layer. The continental crust averages about 35 kilometers thick, meaning that even theoretical maximum depths would not completely penetrate through the crust to reach the mantle below. The oceanic crust averages only 7 kilometers thick, suggesting that deep drilling in ocean locations might reach the mantle more easily. But ocean drilling faces additional challenges from water depth and marine operations. Scientific drilling projects like the Kola Superdeep Borehole and the German Continental Deep Drilling Program encountered unexpected conditions that revealed how little we understand about Earth's deep structure. The Kola project expected temperatures around 100 degrees Celsius at maximum depth, but encountered 180 degrees instead. The rock proved less dense and more porous than predicted, with large amounts of fluid and gas complicating drilling operations. These surprises occurred at depths representing tiny fractions of Earth's radius, suggesting that deeper drilling would encounter even more unpredictable and challenging conditions. The realistic engineering barriers of heat and pressure effectively stop human drilling capabilities around 15,000 meters, as demonstrated by the Kola project struggles at 12,262 meters and the ambitious targets of Chinese drilling projects. The combination of extreme temperature and crushing pressure creates failure modes that attack materials simultaneously through thermal expansion and mechanical compression. Materials experience thermal growth while pressure forces attempt to compress them into smaller volumes, creating internal stress concentrations that guarantee structural failure. These permanent barriers represent more than just engineering challenges. They define the boundaries of human knowledge about our own planet. The vast majority of Earth's volume remains unexplored and perhaps unexplorable, containing secrets about planetary formation, geological processes, and potentially valuable resources that we may never access directly. Our drilling limitations serve as a humbling reminder that despite all our technological achievements, we remain confined to the outermost skin of the planet we call home. The realization that we can barely scratch Earth's surface despite our technological sophistication reveals fundamental limitations about human exploration capabilities. We have sent spacecraft to other planets, developed artificial intelligence, and created materials with properties that seemed impossible decades ago. Yet we remain surface dwellers on our own planet. The depths that lie just beneath our feet contain mysteries that may remain forever beyond our reach, locked away by the immutable laws of physics that govern temperature, pressure, and material behavior at extreme depths. What lies beyond our reach? The vast underground realm that exists beyond our technological reach contains mysteries that could revolutionize our understanding of Earth itself. The mantle, which makes up 83% of our planet's volume, remains almost completely unknown to science because we cannot reach it. This massive layer of hot rock extends from roughly 35 kilometers below the surface down to 2,900 kilometers depth, yet we have never touched it directly. Everything scientists think they know about mantle composition comes from indirect evidence like seismic waves, volcanic eruptions, and meteorites that may represent similar materials from space. The composition of the mantle remains largely theoretical due to our depth limitations, forcing scientists to make educated guesses about materials that could revolutionize our understanding of chemistry and physics. Researchers believe the mantle contains minerals that exist nowhere else on Earth's surface because they form only under extreme pressure and temperature conditions. These materials might possess properties that could lead to breakthrough technologies in electronics, construction, or energy production. Some theoretical mantle minerals could conduct electricity better than any known material, while others might resist heat and pressure in ways that would transform manufacturing processes. Direct samples from depths around 100 kilometers would contain isotopic signatures that preserve records of planetary formation, asteroid impacts, and the gradual separation of Earth's layers. The precise mix of chemicals and isotopes at these depths could reveal whether Earth formed quickly or slowly, how much material came from asteroid bombardment, and when the core separated from the mantle. These answers would reshape theories about planetary formation throughout the solar system. Our inability to dig deep enough limits understanding of Earth's formation by preventing direct observation of the boundary layers between crust and mantle. This transition zone likely contains evidence of the processes that separated Earth's materials by density during planetary formation. The chemical gradients and mineral formations at these boundaries would reveal how quickly or slowly Earth developed its layered structure and whether the process occurred through gradual settling or catastrophic events. The mysteries of plate tectonics remain unsolved because we cannot directly observe the mantle convection currents that drive continental movement. Understanding how hot mantle material rises and cooler material sinks would help predict earthquake timing, volcanic eruptions, and long-term geological changes. Direct observation could reveal whether mantle convection follows predictable patterns or operates through chaotic processes that make long-term prediction impossible. Plate boundary formation and destruction occur through processes that remain largely theoretical because we cannot observe them directly. The recycling of oceanic crust into the mantle happens at subduction zones, where surface material disappears into depths we cannot reach. Understanding this recycling process would reveal how surface materials influence mantle composition and how mantle changes affect surface geology over geological timescales. Geothermal energy potential at extreme depths represents virtually unlimited clean energy that remains untappable with current technology. Temperatures 100 kilometers down exceed 1,000 degrees Celsius, providing heat sources that could power civilization for thousands of years without environmental damage. Companies like Quaise Energy attempt to use nuclear fusion technology to drill deeper than ever before, expecting to find temperatures around 500 degrees Celsius that could revolutionize geothermal power generation. However, even these ambitious projects fall far short of accessing the truly massive energy reserves that exist at mantle depths. The geothermal gradient increases predictably with depth, meaning that unlimited energy exists just beyond our reach. Every kilometer deeper provides access to higher temperatures and greater energy density, but the engineering challenges grow exponentially faster than the energy benefits. Theoretical calculations suggest that accessing mantle-level geothermal energy could provide clean power for millions of years without depleting the resource. China's ambitious project to drill 15 kilometers into Earth's crust represents the current frontier of deep drilling technology. Yet this achievement would barely scratch the surface of the mantle. Even this record-setting depth would penetrate less than half the thickness of continental crust in most locations, leaving the mantle as distant as ever. The Kola Superdeep Borehole reached only 12,262 meters, representing roughly 0.2% of the distance to Earth's center. This means that 99.8% of our planet's interior remains as foreign to us as the surface of distant stars. The realization that we know more about the composition of Mars than we do about Earth's mantle reveals the fundamental limitations of human exploration capabilities. Spacecraft can sample materials on other planets, while we cannot sample materials just a few dozen kilometers beneath our feet. This technological limitation means that our home planet contains more mysteries than the alien worlds we study through telescopes and space missions. Even under ideal conditions, no technology can penetrate beyond 15,000 to 20,000 meters because heat and pressure destroy all materials. The combination of extreme temperature and crushing pressure creates failure modes that attack materials simultaneously through thermal expansion and mechanical compression. Materials experience thermal growth while pressure forces attempt to compress them into smaller volumes, creating internal stress concentrations that guarantee structural failure. Thus, humanity cannot reach the mantle, leaving the vast majority of our planet's secrets locked away permanently. These permanent barriers represent more than just engineering challenges. They define the boundaries of human knowledge about our own planet. The vast majority of Earth's volume remains unexplored and perhaps unexplorable, containing secrets about planetary formation, geological processes, and potentially valuable resources that we may never access directly. Our drilling limitations serve as a humbling reminder that despite all our technological achievements, we remain confined to the outermost skin of the planet we call home. Human limitations create boundaries that may prove permanent rather than temporary because the engineering challenges grow faster than technological solutions. Our ingenuity has solved countless problems throughout history, but the combination of heat, pressure, and distance at mantle depths may represent a permanent barrier that no amount of human creativity can overcome. The question becomes not whether we can eventually reach these depths, but rather what represents the absolute maximum depth that physics will allow. Modern technology can reliably drill up to about 15,000 meters before heat and pressure destroy the drill bit and pipe, far short of reaching the mantle. China's current deep earth drilling project aims to reach exactly this 15,000 meter mark, where temperatures approach 500 degrees Celsius and drilling equipment fails rapidly. This represents less than 0.25% of the distance to Earth center, making our deepest achievements barely a scratch on the planet's surface. Even if money and materials weren't obstacles, physics itself stops us at these depths. Despite all our technological advances, we remain surface dwellers on a planet whose depths will likely remain forever beyond our reach.